Okay, pre-cal students, in this video, we are going to be looking at a very familiar topic called speed, okay? We're all very familiar with that topic. And so let's go ahead and jump right into this. Your heading for today is linear speed and angular speed. Linear speed and angular speed. And later on, I'll be explaining what angular speed is, okay? But for right now, your heading is linear speed and angular speed. And please write today's date down so your notes are organized, okay? Please go ahead and do that. All right, here we go. Now, you are used to measuring speed in miles per hour, kilometers per hour. By the way, if you go north and you go into Canada, at least the last time I was there, their speed limit signs will be kilometers per hour, okay? Feet per second. These different measurements are measurements you're used to when someone says to you, how fast are you going? Okay? Now, these types of units of measure are measurements of linear speed. I would make note of that, okay? So these normal measurements of speed that you're used to, they're classified in a category called linear speed. Now, having said that, it should make total sense that they are called measurements of linear speed. I mean, think about it. Miles, kilometers, feet, these are all units you would use to measure a length of distance, okay? How long is the distance from here to a certain location? Well, it's 30 miles, it's 5 miles, it's 20 kilometers. How many feet down the hallway is the drinking fountain? Well, it's 20 feet down the hallway. So it makes sense that these measurements are called measurements of linear speed because you're measuring something like a line, linear. You're measuring a length of distance, okay? However, now I would write this in your notes. We can also measure speed by using radians, okay? So here we go again, back to the good old topic of radians, okay? You can measure speed by using radians, and this is called angular measure. Angular measure, okay? Let's take a look at this. Take some really good notes, and let me kind of explain to you what we're looking at here, okay? Go ahead and draw a circle, and we're going to call this a clock, okay? So if you want to go ahead and make note of this, it's like it's a clock, and we're going to call this the second hand here, okay? And so go ahead and copy this in your notes, please. And let's pretend now that this second hand started here, and then it moved down like a normal second hand would, and let's say the clock for some reason just stopped right here, okay? Now, based on how long the radius is, we know that the length, the tip of the second hand traveled was 10 centimeters, okay? I'm just making this up, just take some notes on it. I'm not sure what the radius is, we'll just call it R, but we're going to say that the second hand traveled from here down to here, and that length is 10 centimeters. Now, if it's a second hand, going from here to here would be how many seconds? 15 seconds. So do we not have a linear speed like miles per hour, kilometers per hour, feet per second? We have centimeters per second. So what we have is this. We would call this 10 centimeters per 15 seconds. 10 centimeters per 15 seconds. Now, let's take it a step further. With your calculator, if you were to take 10 and divide it by 15, you would get 0.6. So the real linear speed, if you're going 50 miles an hour down the road, you don't say, yeah, I'm traveling 100 miles per 2 hours. You don't say that. You say 50 miles per hour. You take 100 and you divide it by 2. So same thing here. Instead of saying 10 centimeters per 15 seconds, we take 10, we divide it by 15, and we get the linear speed. So what is the linear speed of the second hand? Well, it was traveling 10 centimeters every 15 seconds, thus divide these two numbers, and here's your linear speed, 0.6 centimeters per second. Okay, so that's a linear speed. Now, why did I use a clock to demonstrate linear speed? Well, I'm glad you asked that question, okay? Thanks for asking that question. Because a clock really lends itself well to radians. So I can turn this example over now and use it in radians. So now let's do this same movement, only we're going to look at it in terms of radians, okay? So you might want to draw another circle and take some really good notes, okay? Here we go. Now watch this carefully. Once again, the second hand moved from here to here, and the distance the tip of the second hand traveled was 10 centimeters. Now, we know it took 15 seconds. We got that, so we can go ahead and write down 15 seconds. We know the time. But instead of saying the second hand traveled 10 centimeters, how about if we looked at it in radians? How about if we did this? What if we said, yes, it traveled 10 centimeters, but it also traveled how many degrees? 90, and we should know by now that 90 degrees is the same thing as what? Pi over 2. So instead of saying the second hand moved 10 centimeters per 15 seconds, I'm going to say the second hand moved pi over 2 radians per 15 seconds. Pi over 2 radians per 15 seconds. And this is called angular speed. This is angular speed. Okay, now remember back a page here when we took 10 divided by 15 and we got 0.6. Well, let's do the same thing here. Let's take pi over 2 divided by 15, but let's not use decimals here. Let's keep it exact numbers. So pi over 2 divided by 15 over 1. And of course, when you're dividing fractions, you really multiply and you kind of move things around. So we're going to go ahead and do this. Let's see if we can't get rid of this here real quick. We're going to flip 15 over 1, and now it's 1 over 15. And so when you multiply, pi times 1 is pi, 2 times 15 is 30. So instead of saying pi over 2 radians per 15 seconds, we're going to say pi over 30 radians per second. Now, if you want to divide that into a decimal, that's fine. 3.14 divided by 30 would be 0.105. So you could also put that 0.105 radians per second. And that's called angular speed. So look at the difference, students. One speed was measured with the distance over the time. The other one was measured with the angle over the time. Okay? Now, here's the good news. If this has been a little confusing, understand all that you need to be able to use is this formula right here, and you'll be fine, okay? I mean, we all know about linear speed. Remember in elementary school in Algebra 1, Algebra 2, rate times time equals distance, right? Remember that formula? You should. Rate times time equals distance, divide both sides by t, and rate equals what? Distance divided by time, right? Sure. Distance divided by time. That's what we did back here. We said the distance was 10, and we divided it by the time, 15 seconds. And so, here's a formula for linear speed. And if you're confused about angular speed, use this formula here. You just have your theta, which is your radians. So it's your radians divided by your time. And that's it. It's the radians the object traveled divided by the time that it took. So again, hopefully the explanation I gave you made sense. But if it's a little foggy and you're not really confident, this is the formula you would use right here for angular speed. All right, let's continue on. Let's try to apply what we have learned in these next two word problems. Now go ahead and turn your books to page 555, and let's take a look at example number 6. Page 555, example number 6. Now, if you have to pause the video and turn over there, feel free to do that. I'm going to continue on. The second hand of the clock, I'm reading directly from the book now. The second hand of the clock is 10.2 centimeters long, as you can see right here in the picture. 10.2 centimeters long. Find the linear speed of the tip of the second hand as it passes around the face of the clock. So, here we go. This is really simple to do. Here is the tip of the second hand, and obviously it's going to travel around the circle. Now, think about what I said to you a second ago. Notice it says find the linear speed. And we just talked about, you remember good old linear speed is rate times time equals distance, divide both sides by t, and linear rate is just distance divided by time. So if I want to find the speed of this little dot right here, the tip of the second hand as it whips around the clock, I mean, this should not be difficult at all. First of all, let's go ahead and do this. I know if the second hand goes around the clock one time, that's going to be what? 60 seconds. So there, now I've got the time. To make one revolution is 60 seconds. Now, what about the distance? What is the distance this point travels when it goes around the circle one time? Well, we should know that, guys. How do you find the distance around a circle? Isn't it circumference? Circumference equals pi d, or 2 pi r. Remember that? I mean, think about it. If this little dot right here is moving around the circle and you want to know the distance in centimeters that it actually traveled, then find the circumference around the circle. And when you find the circumference, then you'll have the distance around the circle. So here we go. Circumference equals 2 pi, and then the radius is 10.2. And now you can take 2 times 10.2 and you'll get 20.4 pi. Now I know later on we're going to put 3.1 in for pi, and that's fine. Right now I'm just leaving this exact numbers. So there's the circumference. There's the distance. You just found the distance around the clock, or the circumference around the clock. There it is. So you did it. So now we have rate, or speed, linear speed, equals distance over time. And the distance the second hand traveled is 20.4 pi, and the number of seconds is 60 seconds. And so let's go ahead and use our calculators and type in 20.4 times 3.14 equals, divided by 60 equals, and you'll get this right here. And you can look in the book and see it. You'll get 1.068. We're dealing with centimeters, and that's my fault. I should have written centimeters right up here. Centimeters per second. And there we go. Linear speed. It's that easy. Remember, when you're looking for linear speed, you want distance over time. Distance over time. Okay? All right, let's take a look at one more word problem. And then you'll have some problems to work in your homework, okay? All right, here we go. Page 555, example number 7. Now, first of all, the problem reads as follows. A lawn roller with a 10-inch radius makes 1.2 revolutions per second. Okay, part A, find the angular speed in radians per second. Okay, no problem, here we go. Angular speed, remember, I'm going to put AS for angular speed. Angular speed equals your radians over your time. Okay? Now, we know our time is 1 second. If you'll look at the very first part of the problem, it says it makes 1.2 revolutions per second. Does everybody see that? So my angular speed so far has a 1 right here in the denominator, and I'm going to put sec for seconds, okay? All right, now let's talk about the radians. Did you see how far it traveled in 1 second? Look at the problem. It travels 1.2 revolutions. So here we go. Let's pretend we got a coordinate plane here, and something travels 1 revolution. Now hold it. That's going to be what right there in radians? Isn't that 2 pi? Correct? And then it travels how much more? 0.2. So if I take 0.2, now that's 0.2 of an entire rotation. So I'll take 0.2. Remember, of means multiply. Okay? So I went around 1 whole revolution. Excuse me. We're not in Bible class. Sorry about that. 1 whole revolution. And when it revolves once, that's going to be 2 pi. Then it goes 0.2 more. Okay, so 0.2 times 2 pi would give us 0.4 pi. So we have 1 revolution is 2 pi, and then a little more is 0.4 pi. Add those two together, and you'll get 2.4 pi. Now, if that's a little confusing, I have one more way to show this to you. It's a little easier, okay? If you'll look at the first part of the problem again, it says that it went 1.2 revolutions. So that means we went here, all the way to here, and then a little more. So I'm just simply going to take 1.2, which is the total revolutions, times 2 pi, because that's how many radians I have in one revolution. And if you do that correctly, you will get 2.4 pi. Either way, that is your radians. Now, if I wanted degrees, one revolution would be 360, and then I would take 0.2 times 360 degrees to get the rest of my degrees, and I would get something like, let's see, 0.2, 0 to about 72 degrees, and so it'd be 360 plus 72, but they want it in radians, and so we have it in radians. So there's your angular speed. You did it. You can look in the book now and see how they typed it in. They just left it 2.4 divided by 1, so they just left the answer 2.4 pi radians per second. Now, if I wanted that in a decimal form, then you would type into your calculator 2.4 times 3.14, and you would get something like 7.536 radians per second. So there, we found the angular speed. Please don't forget this formula. Angular speed is the radians traveled theta divided by your time. Now, the next part says find the linear speed, or find the speed of the tractor. In other words, the linear speed, miles per hour. Find the speed of the tractor that's pulling the roller. Okay? And so we can do this pretty easily because we know how fast the lawn roller is turning. And so we can go ahead and do this. Okay? Here we go. Now, don't forget, linear speed is back to your rate times time equals distance. And your rate, or your speed, is distance divided by time. Okay, so here we go. Are you ready? Let's be very careful here. First of all, we know our time is going to be 1 second. Okay, so there we go, 1 second. Now, this roller right here, let's say it starts right here in the ground. Let me get a different color of ink. Now watch this. In 1 second, we know the distance this thing is going to turn is going to be 1 revolution plus 0.2 more. So we've got to find the circumference. And once we find the circumference, then we'll find how far this thing traveled. And by the way, if you were to rip open the circumference and lay it on the ground, the distance this thing travels in 1 revolution is the exact same distance on the ground that the tractor moves. It's the exact same thing, okay? So here's what we're going to do. We're going to have to find the circumference, because remember, in 1 second, the circle turns 1 revolution and then 0.2 more. So we've got to find the circumference. Circumference equals 2 pi r. Now the radius is 10, so I really have 2 pi 10. And of course, 2 times 10 would be 20, so I would have 20 pi. So there's the circumference. So when I make 1 revolution, I know I've traveled a linear length of 20 pi. Now, then I go 0.2 more. So I'm going to take 0.2 of the entire circumference times the circumference. So 0.2 times the circumference, and the circumference is what? 20 pi. And if you do that correctly, you're going to get 2.4 pi. All right? And sorry about that. That's why I paused the video. That's not correct. Let me fix that real quick. What you're going to get is 4 pi. So when you go 1 revolution, the circumference is 20 pi, and then when you go 0.2 more, you get 4 pi. So the total distance traveled is 24 pi. Now, if you didn't like this explanation, then just simply look at it like this. Are you ready? We have what? What is the entire circumference? 20 pi. And it makes how many revolutions? 1.2. So just take 20 times 1.2 and you'll get the exact same thing. You will get 24, and of course there's a pi with it, so 24 pi. Okay, so the total distance the tractor has traveled is 1.2 revolutions, or the lawn roller has traveled 1.2 revolutions, which is how much distance on the ground? Well, it's 24 pi distance, so you have your distance divided by your seconds. So your answer could be one of two answers. You could say the linear speed is 24 pi. Now don't put radians. This is not radians. Remember, this is the circumference. This is the circumference, the distance around the lawn roller, okay? But it would be 24 radians per second, or if you want to take 24 times 3.14, which is what they did in the book there, you'll see you will get 75.4, and it should be inches. So 24 pi inches per second, or 75.4 inches per second, and that would be linear speed. Okay, and that's it. You really need to practice these now on the homework that I'm going to give you. Okay, I hope this has made sense. Again, what we're trying to look at today is linear speed and angular speed. And linear speed is the speed that you're used to. Rate times time equals distance. So your speed is distance divided by time. You're used to that. Angular speed is something new, and it's speed measured in radians, and it's radians divided by time. Radians divided by time. Okay? Call or email if you have any questions.